My name is P.K. Young. I'm from the School of Aerospace Engineering at Georgia Tech. And together with my co-author, Kuan Mafikuma, first I'd like to thank the organizers for putting us on the program, and also Oak Ridge National Lab for enabling our work in our science specialty, which is about study of turbulent fluid flows. And we would like to perform the largest simulations possible that we call extreme scale simulation. And of course, we see the potential of OpenMP. But before we get to OpenMP, let me spend the first a few minutes about turbulence, a little bit about what this subject is, why do we need extreme scale, and then we'll talk about the computing. Turbulence is something that we easy to find in our lives in many kinds of applications. I would say that it's very complex, which is very common and also very important. Some of the examples are the graphics on the screen now. On the left-hand side is the concentration field, essentially color-coded from the surroundings. In the middle, we have a wind farm. And on the right-hand side, we have an airplane. If you look very carefully, taking off and the motion in atmosphere. Of course, here so essentially made artificially colorful. But the complexity is that in all of these applications, there are disorderly fluctuations. The flow has a random or stochastic nature, despite being governed by deterministic physical laws. So even one of the well-known Nobel Prize winners have considered turbulence to be important. And if we want to have engineering devices that are more efficient, you would like to predict extreme weather more reliably, we want to understand airborne transmission of disease agents and so forth. We need to model turbulence, and before we can do the modeling, we need to have some fundamental understanding, which is what the simulations are about. We are trying to solve for instantaneous velocity and the pressure fluctuations subject to the laws of conservation of mass and momentum. These are exact equations called the Navier-Stokes equation. In the simplest case, we have on the left-hand side essentially the acceleration of a fluid element or a piece of the fluid, and on the right hand side, the forces acting on it at a minimum pressure and viscosity representing frictional forces, and sometimes you have some other forces as well. We need leadership class computational resources because of a number of reasons. The flow is unsteady, three-dimensional, stochastic, non-linear, a wide range of scales. All of these are requirements that would add up very, very quickly in terms of the number of grid points that we have, that we must have, the domain size, the grid spacing, and in each direction for high Reynolds number turbulent flows must be very large. And if we want to resolve the small scale better, you want more time steps. And all of these together, the overall operation count increases at least very often more than n to the fourth. So that is to say that every halving of the grid spacing brings us 16 times more computational power. As a result, it's unavoidable that we will run into large node counts, long run times, and huge data sets that we have to deal with afterwards. We need to have high accuracy, but we can make some compromises in terms of the geometry. So we use a method, a numerical method that's well known, essentially the Fourier decomposition, where you have here represent the Fourier coefficient. They are complex values, and if we take the Fourier transform of the entire Navier-Stokes equation, we can rearrange the result in the following form. Where on the right-hand side, the main issue is how do we deal with the Fourier transform of a nonlinear term. And the economical way of doing so is just to perform the modification in what we call physical space, and then take the transform. And that gives us n in terms of cost for each line of data. For a three-dimensional Fourier transform, we're going to have n square of these lines, so that we have n cubed log base 2 of n. However, we have a new problem because of the parallel computing. We need to rearrange data between different parallel processes, so we have to do a transport using MPI all-to-all. And we'll be talking about domain decomposition in a few minutes, but generally, just the all-to-all that is taking the most time. So one may ask the question also. Think about GPUs; they are known for fast computation, but our problem is our greatest problem is in communication. How is that going to help us? Of course, we have some good answers for that. So what are we going to do here from a science point of view? We're going to run a very large simulation. We are primarily interested in first how large the fluctuation can be. How extreme can the fluctuation be? Are they likely and so forth? Well, so we're interested in a quantity called the dissipation rate, which is twice of the viscosity times the quadratic measure, and what's called a local strain rate on a fluid element. You will have a piece of the fluid initially in some regular shape. It's going to get deformed by the turbulence, by the fluctuation. In classical theories, the fluctuation of epsilon were completely ignored. So there is that's an important issue in how do we make the intermittency correction. So, and this is going to be a function of scale size. So we take epsilon, and then we will take a local average around a three-dimensional domain, a subdomain, a linear size R, take it to some power p, and see how it depends on the scale size R. And so then these theta p here those are the exponents that we are interested in. The calculation can be very expensive because we need both high Reynolds number and high resolution. Fortunately, on Summit using CUDA Fortran, we have been able to produce a reasonably a code that performs quite well. 18K cube resolution. That's what I mean by 6 trillion. I'm not going to show all the results, but I'd like to show one research appearing in a paper that is part of a invited collection of papers to be published sometime this month. So here we have several graphs here, and on the right hand side, there are two columns basically. The column on the left of this is about the dissipation rate, and then on the right hand side is the so-called entropy. Entropy has to do with the change in angular orientation of essentially of a local fluid element. This is the simplest turbulent flow that we have for force isotropic turbulence. And the Taylor and the Reynolds number here is an important measure about the size about the range of scale increases by a factor of somewhere between 3 and 4, and the number of grid points are going from 3K cube to 18K cube. We can see that now let's just say at the top row we have the second moment, and then we take we get the so-called logarithmic local slopes to try to deduce the exponent. If there's a well-formed scaling region, then we have a plateau where the curves in the middle would be flat here, somewhere here, and that works quite well for both variables that we're considering. Not as well as fourth order because this is a more challenging problem in terms of the sampling. But what we have found is that in the middle of the so-called universal range of scale, these two variables behave very similarly. That we could not be sure of if I did not have data at a sufficiently high Reynolds number. And then so to go to continue, we are going to try to run a larger simulation, add additional capabilities to the code, and of course we need an extra scale computer and a reliable way of using those computers. So I will turn it over to Kuan.
In the second half of this talk, we would like to focus on the computing aspects of performing pseudo-spectral direct numerical simulations of turbulence, and how we can use GPUs on the newer heterogeneous architectures to get the best performance. And also we will look at how OpenMP and some of the 5.0 features can be used to improve the portability of our code to future architectures. So first we start off by looking at how to perform 3D Fourier transforms using the GPUs. We consider a simple cubic domain with n grid points in each direction, as shown here on the right. We use a 1D domain decomposition or a slabs domain decomposition, where the cubic domain is divided in one particular direction, in the Z direction here, among the P MPI parallel processes, and such that each parallel process holds one slab of data, where a slab of data has multiple planes of data in it. In order to perform these 3D transforms, we copy an entire slab from the CPU, which is the host, to the GPU, the device, and perform Fourier transforms on it one direction at a time. So in this case, we can transform the data in the X and the Y directions directly, as they are both local to each MPI process on the GPU. In order to transform data in the z direction, we would first have to transpose the data, that is, convert the xy slabs to xz slabs, and then perform the transforms in the z direction. Uh, Once these transforms in the z direction are performed, then we can finally copy the data out from the GPU to the CPU. In this approach, the operations are performed in a synchronous manner, and also it requires the entire slab of data to be available on the GPU, which limits the problem size that can be reached. So to avoid these limitations, to basically overcome these limitations, we have come up with a new batched asynchronous algorithm that we presented at the Supercomputing 2019 conference last year. In that approach, what we do is we divide the slab that each process holds into multiple pencils and process each pencil separately on the GPU, where different operations can be taking place on different pencils, and they can also be overlapping each other. For example, in this example shown here on the right, when we are computing on the blue pencil, we could be performing a device to host transfer on the green pencil, and also a host to device transfer on the red pencil, while also doing an all-to-all transpose on the brown pencil, which is achieved by using a non-blocking all-to-all call. So this way we can overlap the MPI, data transfers, and the computations on the GPUs. This code was implemented in the CUDA Fortran and presented at the 2019 Supercomputing Conference. So in this work, what we will look at is porting this code to use OpenMP and some of the 5.0 features. So the first aspect of this work is comes up from the need that we need to have an entire line of data available on the GPU to perform Fourier transforms. So that requires being able to do non-contiguous maps and strided copies. So in the example shown here, we have a 2D plane of data. And since we are working on a Fortran code, the memory is contiguous in the column-wise direction, that is along the x direction. And say, for example, if we want to transform in the y direction, we would need data line of data in the y direction. So that would mean performing strided copies, some elements in x, then striding over some memory, and then copying some more elements in x and striding some more in memory, and so on until all the elements in the y direction have been copied. So this can be done in CUDA Fortran easily by using a CUDA memcopy 2D call, where we can specify unique destination and source buffers, and also it enables us to specify the stride and the number of elements in the column direction to copy. But how do we do this with OpenMP? So a simple way would be to basically map the necessary elements using the map clause as shown here, but such sectional maps are not 5.0 compliant. So a workaround is to copy the necessary elements onto a smaller buffer on the host itself, and then map that smaller buffer to the device. But this requires some additional work on the host, which incurs some performance penalties that we would be better off without having. So what we decide to use is a device memory routine that is part of the 4.5 and above standard in OpenMP, called the OpenMP target memcopy rectangular, which basically allows us to copy a rectangular subvolume from a larger multidimensional array. But this, according to the OpenMP standard, is only callable from C and C++. So we make use of a C Fortran interface to be callable from Fortran. And we also need to take care of the fact that C and Fortran have different ordering, where C is row ordering and Fortran is column major ordering. So that also needs to be taken into account when we pass in some parameters to the target memcopy rectangular call. So here on the right, we're showing a simple example of how to copy the data from a larger source buffer to a smaller destination buffer. Here we are copying particularly the third pencil from the source buffer to the device buffer. So the parameters for the target memcopy rectangular call are the destination and the source buffer, similar to how the CUDA Fortran CUDA memcopy 2D call had. The element size, which is the number of, what is the precision of the data that we're copying, number of dimensions, which is two-dimensional in this case, the volume of data being copied. So in this case, we are copying the all the elements in the row-wise direction and some elements in the column-wise direction. So that would be the volume. The offset would be the number of parameters or the number of elements from the beginning of each dimension. So for this example, since we're copying the third pencil, the offset for the In the column-wise direction would be 2 pencil widths, that is 2 NXP. And then in the row-wise direction, since we're copying from the very first element in the row, the offset is 0. And then the last set of parameters is the dimensions, which is basically the number of elements in the row and the column-wise direction for the source buffer and the destination buffer. So this memcopy rectangular call is blocking in nature. So in order to perform to use the 5.1 feature, which is the memcopy rectangular async, that enables the use of dependency objects, which helps synchronizing with other tasks and makes it more easier to work with other OpenMP tasks that are computing or transferring data to the device and back. So the next aspect of this work is looking at the interoperability between OpenMP and non-blocking libraries. This is because we perform a lot of CUDA FFT or ROC FFT library calls in the code. And in this example, we are showing how to perform a simple forward and inverse transform on a set of data using a non-blocking stream. So here we have a task within which these FFT calls are being called. And we call this task as task A. And then after that, we have on this transform data, we're performing some computation, basically scaling the data by the number of elements in the X direction. The dependencies are set up such that task B will only execute after task A. And or that is what is the intention of setting it up this way. But in practice, what we have seen is that the task A is considered to be complete as soon as these FFTs are launched by the thread that is working on this task to the device. It does not wait for these FFTs to actually start executing on the device. So what that leads to is the task B is actually started before these FFTs actually complete running on the device, and that gives us some incorrect results. So we can see from this simple example that task dependency is not sufficient to enforce the required synchronization. So we make use of a 5.0 feature called the DETACH clause by adding this DETACH clause to the task construct. And then the FFTs are launched similar to what we've seen before. But we also add a hipstream add callback function here, which introduces a callback into the stream in which the FFTs are executing. So now what happens is that once these FFTs are launched, the task is still considered incomplete because this event is still not fulfilled. So once these FFTs actually finish running on the GPU, the callback function that we have introduced into the stream is now executed. And this callback function basically fulfills the event that frees this dependency on this task that later ensures that the task B, which had a dependency on the task A, can now execute. So this way we are ensuring that task B does not begin before the FFTs actually finish running on the GPU. Meanwhile, we could have some operations on in task C occurring at the same time when these FFTs are executing on the device. So this way we can use the detach clause to enforce the required synchronization and also introduce some asynchronism in the code. Next, we look at porting the batched asynchronous CUDA Fortran code to OpenMP. On the left, we have the CUDA Fortran code, and on the right, we have the OpenMP code. So to quickly walk through the CUDA Fortran code, the operations that we're doing here is a 2D copy from the host to the device, FFTs on a buffer, and then the 2D copies again back from the device to the host, while also packing the data, making it ready for the all-to-all transpose that's coming next. The necessary synchronization is set up by using CUDA stream wait event and CUDA event record, such that, say for example, if we are performing the FFTs on the current buffer, CURR, that is only started as soon as the device host to device copy has been finished on that buffer set up by this CUDA stream wait event. And similarly, the device to host copy is not started before the computations on that previous buffer is actually finished to ensure that we are not copying the data out before it is ready to be copied out. So this is done similarly in the OpenMP by using the task depends with an in and out dependencies. And the CUDA memcopy 2Ds are replaced by the OMP target memcopy rectangular. So this way we can port the CUDA Fortran code to OpenMP. And also want to point out here that the detach clause is attached to the task that the FFTs are being executed from. So to briefly present the performance numbers from a non-batch synchronous code, we have collected these numbers on Summit using up to 1,000 nodes and with one task per GPU. The timing provided here in the table is for 3 pairs of forward and inverse transforms. We have data for CPU version, which used all the cores per node, the CUDA Fortran version, and the OpenMP version. We can see that the CUDA Fortran and the OpenMP version are both performing similarly with respect to each other and are showing a speed up of around 2.6x compared to the CPU version, which used all the cores on the node for the problem size of 12K cube. We would also like to point out here that the turbulence simulation code, which is the full-fledged DNS simulation code, which used CUDA Fortran, can run on 3,000 nodes of Summit and can simulate a problem size of around 18,000 grid points in each direction. And this has been shown speed up of around 3x compared to the CPU code, which used all the nodes per node, all the cores per node, sorry. We don't yet have performance numbers for the batched asynchronous code using OpenMP. This is because one of the reasons is that the OpenMP target memcopy rectangular call, which is used to perform the strided copies, are slow and compared to the CUDA memcopy 2D call, and we are currently working on trying to get better performance out of it. And also the asynchronous features that are enabled using the DETACH clause are still under development, as it's a relatively new feature from OpenMP 5.0. In regards to portability, we'd like to point out here that the OpenMP code actually can compile and run on both NVIDIA and AMD GPUs, which makes it a portable code to various architectures. To conclude, I'd like to say that using this high batched asynchronous algorithm, we have been able to perform direct numerical simulations at record-setting resolutions. That has enabled us to get high fidelity results on intermittency and extreme events at very high Reynolds numbers. We are also able to perform some computationally demanding studies of turbulent mixing and particle dispersion using this batched asynchronous code. We are currently working on developing a 3D FFT kernel using the OpenMP 5.0 features to target GPUs. At present, we have a batched synchronous version which enables running large problem sizes, but we are working on porting the batched asynchronous CUDA Fortran code to OpenMP. In the future, we'd like to continue this porting effort and to be able to run very large problem sizes, even beyond the current largest resolution that is possible on Summit, which is 18,000 grid points in each direction. For that, we need the batched asynchronous algorithm to get the optimal performance, which uses OpenMP 5.0 detach feature, and also be able to perform fast strided copies between the device and the host using the target memcopy rectangular call and the asynchronous call of target memcopy rectangular. With that, I would like to conclude our presentation and thank everyone for your attention.